Nowadays, every human on average generates 1.7 megabyte per second. This corresponds to producing about 700 book pages every second. The amount of data that we produce on a day-to-day basis keeps increasing with tremendously high speed. At the moment, about 5% of the world's electricity is used to store our data, and the tendency is increasing. Transistors are the basic components of data processing.
While decreasing in size down to 40 nanometer, the density of transistors on a chip can reach today up to 200 million transistors per square millimeter.
At this high density, the heat created by the transistors cannot easily escape, and a huge amount of energy is needed to cool those devices. In order to support our future needs for data storage and information processing, we require new energy-efficient paradigms. Many research groups worldwide are looking for the game-changing weapon. In the Scanning Probe Microscopy department, we are forging this weapon on the fundamental level. We are exploring quantum phenomena at the atomic scale in novel types of 2D materials. In these materials, the electrons are constricted to 2 dimensions. And this is really a game changer for the physical properties. For example, in 2D magnetic materials, strange magnetic phases, so-called skyrmions, arise. And these phases, these skyrmions, have various potentials to become the basis of our future's energy storage devices. The most popular magnetic material is iron. It is a ferromagnet, and this means it does not require an external magnetic field to show magnetic properties. When we look at the atomic scale, ferromagnets consists of material patches on the length of 100 nanometers, in which the magnetic moments of the atoms are aligned parallel. If we now just take one single layer of iron and put it on a material that has a lot of electrons, for example iridium, then the magnetic structure changes drastically. It becomes a so-called skyrmion lattice. This is different from the magnetic order that we learned in school. The reason is the quantum mechanical interaction between the electrons and the spins in the iridium substrate. This interaction has a significant influence on the magnetic order of the iron layer. The manipulation of skyrmions requires much less heat when compared to our current magnetic storage in hard drives. That's why skyrmions are hot candidates for future energy-efficient magnetic data storage. If we now just add one more iron layer on top, then the magnetic structure of the iron layers changes again drastically. It becomes a so-called spin spiral, basically a one-dimensional skyrmion. And here lies a very powerful handle to control magnetism. By slightly changing the position and number of atoms, the emergence of magnetic structures can be tuned. One key expertise of our department is to develop novel experimental methods to study 2D materials with ultra-high spatial and energy resolution. This requires our setup to operate in ultra-high vacuum and at temperatures close to absolute zero. Recently, we developed a combination of force and current detection to achieve ultra-high resolution of skyrmions and to make their magnetic structure visible atom by atom. In our SPECS setup, an atomically sharp magnetic iron needle is mounted on a wiggling prong, the cantilever. The amplitude is really small, about the size of an atom, and it oscillates more than 30,000 times per second. When we bring the needle close to the magnetic structure at the surface, different types of forces start to act on the tip. At large distances of about 50 nanometers, these forces are not atom-specific and do not provide high lateral resolution. When the needle is as close as 0.5 nanometers to the surface, then quantum mechanical interactions dominate. This has 2 main consequences. First, even though the needle and the surface do not touch each other, the electrons can flow in between them when some voltage is applied. This effect is known as tunneling current. Because the electrons are injected from a magnetic needle, the amount of tunneling current depends on the orientation of the magnetic moments of the last atom of the needle and the magnetic orientation of the atom on the surface. The second consequence is that the electrons in the needle and the surface start to interact. Electrons are quantum mechanical objects and can be described as delocalized clouds around the nuclei. Depending on the exact distance, these electron clouds can attract or repel each other. Because both the needle and the surface are magnetic, we can measure the difference in the magnetic exchange interaction depending on the orientation of the spins of the electrons. By combining both effects, we can image, for example, skyrmions with ultra-high spatial resolution. 2D materials do not only host unusual magnetic phases. The squeezing of electrons into two dimensions also results into charge ordering and novel types of insulating phases. And these phases are puzzling us physicists because we often cannot describe them within our theoretical models. In our department, we strive to describe and understand these phases. For example, charge density waves.
A charge density wave is a strange charge ordering phase seen in 2D materials. In an STM topography, it is visualized as a modulation of the electron density to form superlattices on top of the atomic lattice. My PhD project is to investigate the extent of electron-electron interaction in the formation of charge density waves. I am using a combination of different scanning probe methods based on force and current-based detection to understand the electronic and geometric properties independently. If we are able to understand the role of electron-electron interactions, we can predict the different quantum phase transitions and also design different quantum materials for particular functionalities.
The goal of our research is to gain fundamental understanding of the electron-electron interactions in quantum phases of 2D materials. Our approach is to develop novel experimental techniques with atomic scale resolution to study the interplay in between the geometric structure and the electronic and magnetic properties. And we are continuously looking for master students and PhD students as well as postdocs to join us on our mission. That is, to explore game-changing 2D material systems for a development of our future energy-efficient electronic devices.